So this is maybe lead-in talk to the actual theme of the conference. We're very pleased to have Hans-Joachim Hein, who will speak on ALG and ALH, what we really know.
Thanks. Thanks very much for the invitation. So this is going to be a reenactment of a talk that I used to give a lot, maybe 4 or 5 years ago. So some of you have seen this before, and I do apologize. But on the other hand, that's this stuff is more or less the only overlap between me and the topic of the conference. So that's no excuse. So I'm going to be talking about gravitational instantons. Might mean different things to different people. So I'm just going to clarify what I mean by that. So gravitational instanton for me is going to be a four-manifold, a Riemannian four-manifold. I'd like to assume that it's simply connected, so it's a convenience for me, so I don't have to distinguish a lot more cases. And the key condition is that the homonymy group, the Riemannian metric, is SU2 or SU1. So if you have a Riemannian four-manifold which is complete and simply connected, then if it doesn't split as a product of something lower dimensional, it homonymy has to be either SU2 or SO4. So holonomy SU2 implies, pretty obviously, that the manifold is hyperkähler. So this means that there exist 3 parallel complex structures, and actually a whole 2-sphere parallel complex structures. I'm just going to write down 3, I, J, and K. So those are going to be parallel complex structures, and they satisfy the quaternion relations. I squared is J squared equals K squared, because I, J, K is -1. The third condition I want to impose here is a finiteness condition, so that the curvature tensor, the Riemann curvature tensor, is finite L2 bar. So that's a very natural condition in dimension 4 for various reasons. I'm going to mention one right away, is the scale invariance. If every scale Riemann metric, then the L2 of the curvature stays the same. I'll make a couple more remarks. The first one is that so when I started studying this, I wasn't primarily interested in hyperkähler geometry per se. But the thing I found most interesting is that hyperkähler implies Ricci flat in all dimensions. I was interested in Ricci flat manifolds and Einstein manifolds. So that's a local calculation in any dimension. It implies Ricci flat. The second remark is again about this finiteness condition here. So for all we know, finite L2 norm of the curvature is the same thing as finite topology. So being homeomorphic to the interior of a compact manifold with boundary for gravitational instantons in hyperkähler. So conjecturally assuming all the other conditions, the Riemann curvature is finite L2 norm. Manifold is finite topology. Yes,
Yeah.
yes. And the reason for this is the Gauss-Bonnet formula in 4 dimensions. So if you have, so if you assume that you have a compact manifold, a compact Einstein manifold without boundary, then the Gauss-Bonnet formula says that the Euler characteristic can be written as 1 over 8 pi squared times the L2 norm of the Riemann curvature tensor. M4 is closed in Einstein. And then if you start thinking about how things work out on non-compact manifolds, that's a reasonable thing to conjecture. And certainly not, we certainly don't know any counterexamples to that statement.
Can I ask a question?
Yes, sure.
I don't know much
Yeah.
maths, I'm probably in the wrong room. In the physics literature, there was a recent example that appeared, which was the Gibbons-Hawking ALF space,
Yes.
but with an infinite number of
Yes.
centers
Yes.
all sitting along a line.
I think that thing's going to be infinite.
Yeah, so I mean, so the ALE, the version where you
Yeah.
don't add on the constant to the
Yeah.
potential, that was something that I did with around 1990 with, and you could certainly add a constant on that without changing the version of the series, but it's,
But it does have divergent Riemann tensor square.
yes, yes.
Oh, the integral is
Yeah, the
divergent.
integral is divergent. The integral is divergent.
Thanks.
Right. So that's actually. I mean, okay. So I don't have to write that down anymore. Thanks. That's great. So you have these infinite monopole examples that you can write down explicitly. Whether the integral of the Riemann squared is actually infinite, and we do have infinite topology. So it's not automatic. And the other thing, so the one thing we do know, so this is going to be important later on. So from work of Chibertian, I think it was 06, we know that finiteness of the L2 norm implies that the curvature actually behaves quadratically, that all sectional curvatures behave quadratically. So the space has to be asymptotically flat in that weak sense. So this is true more generally if you have a complete Ricci flat form manifold. You don't need it to be hyperkähler. So this is a theorem about the Einstein equations. This is for complete Ricci flat. So then I want to try and review what we know about the classification of gravitational instantons. So what possibilities are there? What types? And there's a rough invariant we can use to classify gravitational instantons, and that's the volume growth. So that's not actually a well defined invariant per se, but so I'm going to say that the volume growth is equal to beta. So beta is a real number. If the following holds true, if I take a geodesic ball of radius r, set it at some fixed point in the manifold, and then look at very large radii, the volume is supposed to grow like r plus beta, like that fixed power of r. So a priori, there's no guarantee that this is a well-defined number. So it could, volume could grow differently in different regions of the manifold, but in all the examples we know it is a well-defined number. It's independent of the base point also. This is r goes to infinity.
So your gravitational instantons have only one end?
Yes. flows from the splitting theorem of G-Gromont, because they're Ricci flat. I mean, they could have two ends, but then they have to be cylinders. But the only way to be two-ended is actually to be a product R cross T3 in this case.
You can always get a line joining two
Yeah.
ends.
And the line has to split off. So it's not a priori clear that this rate is actually a well-defined number, but what we do know is that so if you assume that the volume behaves like R to the beta, then we can say that beta can't be arbitrary. So the volume comparison theorems in Riemannian geometry give us constraints of beta, and tell us that beta has to lie between 1 and 4. The upper bound is more or less obvious from the standard volume comparison theorem, but the lower bound is slightly less obvious, but it's still basically just a volume comparison theorem. And both of these bounds are true much more generally between 1 and n for n-dimensional manifolds of non-negative Ricci curvature. So I'm not really using the Ricci flatness in an essential way. So the classification starts at the largest possible value here.
So in your definition, you said complete, but you failed to say non-compact. That's where the one comes from, it's non-compact. That's right.
Union 0.
Union 0. I'll do that.
Sorry to be a troublemaker.
That's okay.
It's like the annoying student that always asks about the empty set.
But anyway, it's going to start with beta equal to 4, and it would have taken me some time to get down all the way to. Right. So this case is completely understood. So this is very nice. So first of all, for the finiteness of the L2 norm, this condition is automatic. So just assuming complete hyperkähler of Euclidean of maximal volume growth R to the 4 implies finiteness of this integral automatically. So this is from work of Chi and Tian. So we have this for free. And once we have this, there's some regularity theorems that tell you that the manifold actually has to have a lot of structure at infinity. Just having this curvature bound. So this is something people Bandukas written in Nakajima around 1990. So we get that the manifold has to be ALE. Asymptotically locally Euclidean then necessarily. So what this means is that infinity basis model on a flat column. We have S3 is gamma, and gamma is a finite subgroup of SU2 acting freely on S3. It doesn't stabilize any lower dimensional subspaces, and it's going to be true that the Riemannian metric converges to the cone over this space form, our cone of R4 modulo that will have a polynomial rate. The end of the manifold has a very simple structure necessarily. So this is true in the metric sense. What this means is that you can find a diffeomorphism between your manifold minus a compact set and the cone minus a neighborhood of the origin, so that with respect to this diffeomorphism, the hyperkähler metric converges to the flat cone metric and a polynomial rate. Phi star G minus flat metric. It's going to be of R to the minus 4 actually. The diffeomorphism from R4. Modulo ball. necessarily an ALE space, then Cronheimer classified those completely. So there's sort of uniform way of constructing these spaces, and you can show that the list that you get in this way is exhaustive. And all we needed here is that complete hypercalar of Euclidean volume growth. So in this case, we don't have a complete classification that's anywhere really as nice. There's a couple of years ago, there was very interesting work by Nozomi now. Gives off a lot of positive results towards classification. So this was Merv a couple of years ago. So what he showed is that first of all, beta has to be equal to 3 necessarily. And a priori, beta is just a real number. If you assume that it's strictly less than 4, but at least 3, then it has to be exactly equal to 3. I mean, roughly speaking, if the volume grows less than at the maximal rate that it possibly could, you have to see sort of circles at infinity along which the manifold gets compactified. There's no freedom for continuous parameter there. Either it grows like Euclidean space, or one direction is compactified, so you have this gap there. But we'll see that this logic sort of breaks down if we go down to lower rates. But here it actually works, so the volume growth has to be equal to 3. And so I mentioned these circles. It turns out that you can actually make this rigorous, and you can show that if the curvature decays just a little bit faster than quite rapidly, so if you have the Riemann is actually of 1 over r to the 2 plus epsilon. So we always have quadratic decay from Cheer and Tian, and I'm saying that if I assume just a little bit more, just an epsilon more, then I actually get this nice structure at infinity that I see these circles. So that's the counterpart to this picture. Here's when manifold is no longer ALE, but it's going to be what people call ALF. So you're asymptotic at a definite rate to some nice explicit model space at infinity, and the model space is basically a circle bundle. So I'm not going to write down the precise definition because it's slightly complicated. Roughly speaking, you're going to have something like this. This makes any sense, but there's a compact part in the interior where you don't know anything, and then as you go out to infinity, you see a circle bundle where the circles have asymptotically constant length. And the base of the circle bundle is going to be a flat 3 manifold. And it's an S1 bundle asymptotically. Base is flat, and there's only 2 options here, so either we have R3 minus a ball, or R3 minus a ball, modded out by Z2. So the cone over the projective plane. So that's the only 2 options for the base. So that's what he proved. And in the first case, he went even further, and he showed that assuming that you don't have this extra Z2 action at infinity, so assuming that you're really fibering over R3 essentially, you get a complete classification. This is also due to mirror. And there basically what you get is the examples that you mentioned, so the multi-top nut spaces.
With finitely many centers.
With finitely many centers, that's right. Here the picture is not so clear. So there's a conjectural classification in this case, but I don't think.
You also have AV classification? Like
No,
Here you only have A and D. You have two infinite series.
A and
So this is the A series. This is sort of multi-top nut. That's sort of the same thing as the ALE spaces of type A, except that you're adding on like +1 to the harmonic function, and this is more complicated. So most of them have the same asymptotic models as an ALE space of type DK, except that you deform the circles. But then there's sort of sporadic ones, 2 or 3 that don't fit.
In the D case, do you also get cubic curvature decay?
Yes. But that's fairly obvious just by making, everything has to be given by
Yeah,
harmonic
so
functions to leading
that's a
order.
very good point,
Yeah.
yeah. So the naive answer that you might expect in the second case would miss the Atiyah-Hitchin example, and makes one worry maybe there are other things that are missing.
Yeah, exactly.
I'll stuff out then.
So Atiyah-Hitchin and double cover of Atiyah-Hitchin both sit in the second.
Down here, that's right. So let's say I'm just talking about the double cover of a Atiyah-Hitchin because I want to assume that my spaces are simply connected. That's exactly what I was talking
I
about
see.
before. So Atiyah-Hitchin would sit down here, and that's not sort of the same type as the DK ALE spaces, so sporadic in some sense. But it exists. So that's probably the reason why we don't have a complete classification here, because we don't even have a uniform sort of convincing construction, or sort of exceptional cases.
That's the wrong side of the nut parameter and things like that.
Yeah.
It's very strange.
So then for volume growth rates strictly less than V, so I want to mainly write down the theorem, write down and explain the theorem that I proved a couple of years ago, which is an existence theorem. It gives sort of uniform classification of a large family of examples that in particular contains all the ones that were known to exist before. So there's a nice uniform picture there. At least hope that the picture is actually complete. The term takes a while to state and explain. I'll save it first. Lots of remarks. Construction starts with a rational elliptic surface. Say a little bit more about what that means later, but the basic picture is that you have a compact complex surface, X, that's fibered over CP1 over the Riemann sphere, so there's a holomorphic vibration F, and the fibers are related curves. So generically, the fibers is going to be a smooth, complex torus, and then you have exceptional values where the fiber is something more singular. I'm going to single out one particular fiber here. That's something that I want to remove. So I want to look at the complement of one particular fiber in the rational elliptic surface. So far, the only thing I've defined for you is an elliptic fibration or CP1, so I haven't exactly said what the word rational means. It more or less means that X is actually a rational surface in the usual sense. So it's a blow up of CP2, but I'll be a little bit more precise about that later. So the fact that it's a rational surface allows us to do the following. So we can take a meromorphic proof form. Whose divisor of poles and zeros is just minus d. So it's a meromorphic proof form on the surface that has a simple pole along a fiber that is regular and non-vanishing everywhere else. So once I fix the fiber, there's exactly one such thing up to scale. This existence is unique up to scale. This turns out that this vibration that I'm talking about, the vibration of my surface over CP1, is actually the anti-canonical pencil of the surface. So it's a linear system given by minus kx. In other words, the anti-canonical bundle of the surface is just the one-point line bundle in CP1 pulled back under the vibration. So that's why I have something like this for every fiber, given the fiber that is unique up to scale. Let's see, what else do I need? I need a scalar class on X.
From your picture, it's not clear. Is the generic fiber or is
It's arbitrary. It can be smooth or degenerate. That's exactly the point, right? Any fiber. So the thing is that once I fix these data, then there exists a Taylor form omega representing the restriction of this class to the open manifold. So M is a complement of this fiber. That's a Taylor form. Such that omega squared is equal to capital omega, which capital omega r. So the Hermitian square of this holomorphic volume form, and that's just the volume form of the associated Riemannian metric. And this is precisely the Calabi-Yau equation. So this guarantees that your Taylor metric that you've constructed here is Ricci flat. This means that the Riemannian metric G is associated with dimension 4 and we're simply connected, this actually means that the metric is hypercalar. But this is strictly 4-dimensional phenomenon. So I don't want to state the n-dimensional generalization.
Omega is unique.
Say it again?
Omega is unique.
if you impose asymptotics, so what happens here is that you write down a model metric on your surface in the neighborhood of the fiber. You're requiring that omega is asymptotic to that chosen model. So if you have two omegas in the same scalar class, they're asymptotic to the same model metric, then they have to be the same. But that's not saying that there could exist some completely different Ricci-flat scalar metric in the same class with completely different asymptotics. That actually happens on C2 even. So, not at the Euclidean metrics, so they're completely different at infinity, but they're Ricci-flat scalar metrics with the same volume form on the same underlying complex manifold.
So that's going to be harder in the case when the D is singular, I guess.
Uniqueness?
Existence, I would think.
Right. I mean, you have to write down more complicated models. We're going to describe the models depending on how singular D is.
The uniqueness is just the Calabi arguments that
Pretty much. Seeing that the Ricci-flat, I have a Ricci-flat Riemannian metric. This identity here already tells me that it has to have infinite volume because capital omega has a pole on the divisor. So if you integrate both sides over the manifold, you get infinity. So it's Ricci-flat of infinite volume. The stronger statement is it's actually
typical subtlety about this is that let's say on C2, when you solve this equation, both the Taub-Nut and the standard flat metric are solutions of that equation with exactly the same volume form.
Right.
So it's
so on
the
C2,
same
so on C2, I mean, what you want to solve is that the determinant of d squared u by dzj, d bar k, so take k, go from 1 to 2, this is constant equal to 1. That's the equation you want to solve, and then u is going to be the scalar potential of your Ricci-flat metric. You're looking for a plurisubharmonic function u satisfying this Mohr-Ampere equation. What Carl was saying is that there exist two completely different solutions. So the obvious one is u just equal to radius squared, which is a Euclidean metric. And then the other solution is some horrible mess that Claude wrote down.
Which polynomials go?
It's implicit. It's implicit. So you have some polynomials, some exponentials, and then it's implicit in terms of those you still have to invert. Actually, Calabi once told me about yet another way of constructing solutions to this equation, which is to use the Bieber-Bach maps. So there exists, C2 is biholomorphic to a proper subdomain of itself. So it's something that you can't have in a complex dimension 1. And then what you just do is, if you pull back, you take the standard flat metric, which is a solution to this equation, the standard potential, and you just pull that back by a Bieber-Bach map, and then you get.
But the solution's not complete then.
Yeah, the solution is, metrically just a restriction of the Euclidean metric to that proper subdomain of C2. So it's not a complete solution.
So if you're just thinking of it as a problem in PDE, then that's a completely honest answer, but differential geometry is something.
Right. So as a PDE problem, the bizarre thing is that if you replace the complex Mohr-Ampere operator by the real Mohr-Ampere operator, so if you put the determinant of the full real Hessian here, then you have uniqueness unconditionally. So then U has to be quadratic polynomial. That's also a theorem of Calabi. Dimension up to 5 or something. Right.
So this equation has two solutions or more? Can have more?
Many. I mean, I just told you a trivial way. If you have like f from C2 to omega biholomorphic,
different omega.
You, maybe.
U is a proper subdomain, then you just take U to be equal to F star once it's squared. Just a pullback of the Euclidean
That's
metric.
not complete solution.
That's not complete.
For complete, avoir une équation.
No?
So in particular, I mean, you're trying to, I mean, these two are distinguished by the fact they have different volume growth. I mean, is it clear that the volume growth would have to be at least cubic if you had a solution?
No, that's not
I
true.
mean, anybody's proved anything.
I don't think so. So then I was going to tell you about what these metrics actually look like geometrically, what the asymptotic model is, depending on what the singularities of the curve are that are removed. I'm going to write down 4 cases. The first one is the easiest, so that's what you would expect. If the thing that you remove is just a smooth elliptic curve, so the generic thing you can remove. Just something like this. This is your compact part. Away from the compact part, the metric is asymptotic to a cylinder. It's the obvious cylinder that you see here. It's R plus cross 3 torus. So you have a diffeomorphism from the model cylinder into your space minus a compact set with respect to which the metrics converge exponentially. For some positive epsilon, the cylinder metric here is just the R squared plus the theta squared. Theta is an angular coordinate on S1, and then you add on a metric on the divisor. So your divisor is an elliptic curve that has a well-defined flat metric that's sort of singled out by your Kähler class, and that's a cylindrical model. So I've told you everything except for the length of the circle, but it turns out that the length of the circle, so the Riemannian length, is determined by your choice of capital omega. So here you're fixing the Kähler class, but capital omega is not completely fixed, it's uniquely up to a scale. So you can scale up omega without changing the Kähler class in this theorem. That gives you one additional parameter. And that parameter in this case is precisely the length of the circle. So in this sense, even in this sense, you have non-uniqueness in the Kähler class because you can be asymptotic to sort of S1 cross T2.
Beta is equal to 1 in this case?
Say it again?
Beta?
Beta is equal to 1. This is what you refer to it as ALH spaces. Second case, I'm going to assume that B is singular of finite moduli. Tell you what finite monodromy means in terms of the picture I'm going to draw here. So then you have your compact part. And the model goes like this. You start with a two-dimensional cone. That's sort of the base of your vibration. So up here in the ALH case, it's sort of one-dimensional. The only non-compact direction was one-dimensional, the rest was compactified. So here you have two non-compact directions, and the model is just a flat two-dimensional cone. And the base is going to be a circle of length 2 pi gamma. I'm going to list the possibilities for gamma in a second. And then over that, you still have your torus vibration. So imagine that this is basically crossed with a two torus. It's a flat two torus of constant size, but the product here isn't an honest product, and this is precisely where the monodromy comes in. So monodromy means that if you take your flat torus and you go around the cone once, so the generator of in the fundamental group of the puncture cone. So if you move your torus around the puncture once, then you get glued back to yourself, not by the identity, but by the finite, by an isometry, by a non-trivial isometry of finite order.
What are the possible modalities?
Exactly the possible finite automorphism groups of an elliptic curve. So it's either Z2, Z3, Z4, or Z6. Because if you have a curve, if you have an elliptic curve with a finite automorphism group, and that automorphism group is going to preserve a flat metric on the elliptic curve, so you can glue by isometries. And it turns out, sort of by inspection of the list of possible cases, turns out that all of these possibilities are actually realized in rational elliptic surfaces. And gamma can be either 1/2, 1/3, 2/3, 1/4, 3/4, 1/6, 5/6, depending on what the monodromy is. So this is 7 numbers here, I hope. Those come in obvious pairs. And there's one exceptional here. And that's exactly sort of the 7 types of singular fibers of finite monodromy in Kodairo's classification of singular fibers on elliptic surfaces. And there's sort of, there's a duality between the fibers. This one is dual to itself. So the one with the 1/2 is just a standard fish tail. That's dual to itself. And then you have 3 dual pairs. And the corresponding angles on the base of the space that you get here is gamma. It's these dual pairs. So in one dual pair, the denominator is the same. The numerators are complementary.
Have you normalized here, so there's some.
There's an inside and an outside of that circle, so it's oriented.
What do you mean by normalized?
You've got a length of the circle, so I mean.
Oh, I'm sorry. What I'm saying is this thing here is the. Right, so it's a cone over a circle of length 2 pi gamma. So that's scale invariant. It's a scale invariant statement. If you just scale, it stays the same cone.
And beta is 2.
Beta is 2. And this is so again. This is just the asymptotic model, and in this case here, the errors were exponentially decaying, and in this case, they're going to be only polynomially decaying. So you have this model plus all factor minus some errors. ALG spaces. And unfortunately, there's 2 more. Unfortunately for you, really. Singular of specifically, one assumes that the monodromy is generated by 1B01. So topologically, if you take the torus fiber, if you go around the puncture, so the basis of H1 of the torus gets transformed by this matrix in SL2Z, that's what I'm assuming. And it turns out that you can have every B between 1 and 9 here. By classification, that's the possible cases in a rational elliptic surface. Then the model is going to be, so again you have the sort of fibration, but now the base of the fibration is not a cone or a line, it's going to be paraboloid, essentially, the paraboloid of revolution. The torus fibration setting over it, but the fibers of the tori don't remain constant. I mean, the torus fibers don't remain constant in size anymore. So what happens is that they get stretched as you move on to infinity. But at the same time, because the area is fixed by the Kähler class, all these tori have to have the same area. So if the other direction in the torus shrinks at the reciprocal rate, so that the area remains constant. So they stretch in one direction, but then they get thinner and thinner in the other direction.
So this kind of automorphism is symplectic, but not homomorphic. Right?
Yeah.
So
Not isometric, because it's a holomorphic isomorphic. It's a holomorphic map, but it's not isometric. It's area preserving, as you say. So that's sort of the moral reason why the tori can't stay constant in length or constant in size, because the Blue map could never be isometric in this case. The volume growth in this case is 4/3. There's nothing mysterious about it. That's just the volume growth rate of a paraboloid, if you compute it out. So the tori don't contribute to the volume growth again, basically because the area is constant. You have Riemann submersion here. So by the co-area formula, all the area growth comes from the base. And so they expand and contract at rate arbitrarily plus minus 1/3. So that's, yeah.
So what happens to your injectivity radius as you go out to infinity?
Well, it's r to the minus 1/3 roughly.
So
It sort of comes from the shortest closed geodesic in the fiber. Because here, down here, the injectivity radius stays positive, obviously, so you can just take a unit ball here. So if we unit ball in the fiber, cross them, get a rough unit ball up here, but the volume goes to 0 at this rate.
In example 2 and 3, both, where can you see this sort of, where the fiber is infinity, where is that sort of?
Not at all, as far as I know. So that's the strange thing about the
You can write down the explicit logometric model, right?
Yep. But that's why it works, because you're using the elliptic fibration structure, you're able to write on the explicit local model. That doesn't really correlate with the singularities of the divisor that you blew in a nice way, at least not that I can see. So if you wanted to start thinking about the problem in terms of, I have a singular curve in the surface, with I don't know, ordinary double point singularities or worse singularities, then don't think, as far as I know, that the type of the singularities of the curve that you're removing tell you much about what sort of metric you could expect from a complement.
But even just the other way around, geometrically, so you've sort of drawn a picture.
Yeah.
Where do you go out in infinity to see that point?
That's exactly the point. You don't. It's homogeneous in the T2 directions, whereas the divisor acoustic intercompacted plot is not homogeneous under T2. So in this case right here, first of all, I'm going to call it ALH star. So in this case here, the divisor is going to be sort of the most degenerative it can be. So it's going to be a cycle of rational curves with ordinary double point singularities. If your cycle has exactly the cycle. one cycle just means that you take a torus and you pinch off a circle, or you take a sphere and glue it back to itself.
And so this is a context where Gromov-Hausdorff type of limits, you know, the differential geometric limits don't stack up very well with the ones that come out of algebraic geometry, out of complex geometry.
Unless there's some sort of extra data on your space that you could use to read out the structure at infinity, but I haven't found that structure yet. Just from the metric, it looks like a homogeneous translation invariant torus. So what's interesting about these spaces is that if you go and calculate the Riemannian curvature tensor, that's going to decay exactly quadratically. So it shows that this bound of Chi and Kian is sharp. So in general, you can't improve even by an epsilon or by a log. If you want to prove statements like this, I mean, you write down a model, and then you have to prove that if your true solution approximates the model to sufficiently high order. For the model, you can just calculate explicitly that this is how the curvature decays, and then you have to prove that your true solution decays to the model sufficiently fast, so that this estimate is preserved. So this is your asymptotic model, and the errors. So first, you have to prove that the errors decay at some rate, and the rate is e to the minus epsilon times r to the 2/3. It's somewhere between exponential and polynomial errors, but it's closer to the exponential errors. Paraboloid is closer to a cylinder than a cone, so that's what I call an ALH star. That's these guys. And then there's one case left.
What are all possible known values of beta?
On the
All possible values of beta, known values of beta.
exactly the ones that I'm writing down for you. Others aren't known. But there's no a priori argument that tells you that beta has to be this, or there's no restriction. There's no general restriction on beta that I know of, except that it has to lie between 1 and 4.
So
Which is
below
much
3,
more
you're saying
general.
there's no.
Yeah.
there's no- yeah.
Yeah. That's their fourth case. So this is.
Interestingly enough, there are various constructions, and they always come out with these values, so it's.
That's because of hyperkähler rotation, ultimately. So if I had more time, I would talk about this.
Okay.
So there's sort of seemingly different examples that have the same beta, which is 4/3. But the thing is, I mean, I've done something hard, right? I want to construct hyperkähler metrics, but in the construction, I've singled out one particular complex structure. I started with a complex surface and constructed a metric that's a priori Kähler with respect to that complex structure. And then because it's also Ricci flat, it's miraculously hyperkähler, and therefore there's all these other parallel complex structures. So it turns out that, you can have seemingly very different constructions of the same hyperkähler metric because you started with very different complex surfaces. You singled out different complex structures to begin with. And for all I know, that's the reason for all of these coincidences that we observe, that we're sort of secretly constructing the same example, but we're starting from different complex structures.
Do you have some suspected values of beta for which there is no known construction, but you still suspect it's...
No. You know, it's- That's again a case with infinite monodromy, but now the map is going to be minus the one I had in the previous case, so it's -1 B01. And it turns out that if you want a rational elliptic surface, then the only possible values of B are from 1 to 4. One more of
Sorry,
these.
I
Yes.
I didn't catch what that picture of
Yes.
the up there with ALH
Yes.
star is. That you said, what was that picture?
Right, so that's a picture where you start with your elliptic surface. And that picture here is the singular fiber that you're removing.
And that's the one that has infinite motion.
That's right. before I only drew a picture with one node.
Yeah.
But you can have up to 9.
I'm sorry, that's B, that's the same as B, that's.
Yeah, that's right. Yeah, that's the same. And then more of these. So in this case, it turns out that your model on the base is again a cone, a flat two-dimensional cone. But in this case, there's only one possible angle, where this is 1/2, and that's ultimately the -1 here. But you get a cone and not a paraboloid. Strangely enough, well, that's how it works out. And in the vibration has the same basic feature as before, that you have these tori of constant area that are getting longer and thinner. And the rate now is log r to the plus minus 1/2.
Awesome.
Obviously, sometimes all these ALGs start. There's 4 of them, 4 types. 4 topological types, basically. Metrically, again, you don't see the B. A priori, so the metric model works the same way with an arbitrary B here. And the picture is, the B only shows up in some coefficients of the relative, sizes of the components of the metric. So you don't really see the B geometrically. So let's see. So the errors compared to the asymptotic model are polynomial again in this case. And if you go and compute the Riemann curvature tensor, this is going to be like 1/r squared. Log r. So it's no longer 1/r squared sharp. You're doing a little bit better than this, but not by a polynomial rate, so you'll only gain the log r. So that's statement of the theorem. So there's a lot more that I wanted to explain. Out of time, so I'm just going to say one more thing. This is I haven't been working on this for a couple of years now, and recently, so this May actually, there wasn't preprint on the archive by Chen.
Al Chen and
Yeah.
Shishang.
One is a student of the other.
But they're unrelated.
They're unrelated. All I know.
Oh, they are.
This is being recorded, so stay here. So in that paper, they showed that if you're in the situation that I'm talking about here, you have a gravitational instanton of volume growth rate beta strictly less than 3, then you would hope that you can show that these guys are the only ones. I'd be very happy if somebody could show that. They can't quite show that exactly because of these cases 3 and 4 with the infinite monodromy, where the curvature decay is fairly slow, 1/r squared and 1/r squared with r. What they show is that if you assume a little more, so if you assume volume growth strictly less than 3, and curvature decay like 1/r to the 2 plus epsilon, so quadratic plus an epsilon better, so like in Minerva's theorem, then you actually do get this ALH or ALG asymptotic structure, and then there's an elliptic vibration on the thing with respect to one particular complex structure. So I haven't read the paper yet, unfortunately.
But does it mean that the compactification is one of those rationality services?
With a little bit of extra work, yeah, but that's I mean, so they show that the asymptotic structure of the metric is like this, and that's the hard part. This uses a lot of Riemannian geometry and sort of collapsing theory, so this is really technically difficult. But once you have that the structure is like in one of these cases here, it's not that hard anymore to construct an elliptic vibration, because an elliptic vibration over C is just a holomorphic function. So you just have to produce one holomorphic function on your space. Then you get an elliptic vibration, and then you automatically get that the thing can be compact defined as an elliptic surface, certainly, and then you need some extra nonsense to say that the surface is algebraic and rational, but that's sort of boilerplate. That's well known. So the hard part is to say if you have volume growth strictly less than 3, and if you assume an epsilon better curvature decay than this one, where R2 plus epsilon, then these bad cases 3 and 4 don't look